In this video, I'm going to show you how to set up some non-standard linear programming problems. The first one is a non-standard maximization problem. We want to maximize p equals 5x minus 8y, subject to the constraints 2x minus y is greater than or equal to 8, 5x plus 3y is less than or equal to 2, 4x minus y is greater than or equal to 10. So we have mixed constraints in this problem. Mixed constraints means that some of our constraints have greater than or equal to symbols. Some of them are less than or equal to. So remember, this is not a standard maximization problem where all of the inequalities have to be less than or equal to. It is a non-standard maximization because of the mixed constraints. So the first thing we need to do is to set up our linear system of equations. So we start with the first constraint. We have 2x minus y, and then over here I'll put equals 8. And because in the original inequality, the left-hand expression 2x minus y could be greater than 8, but now it has to be equal to 8. If it was greater than 8, we would have to actually subtract some unknown quantity, which I will call r. And so that is our surplus variable. In the second inequality, 5x plus 3y, 2, we're going from a less than or equal to an equal to, which means that 5x plus 3y could have been smaller than 2. And if it was smaller than 2, but now it has to be equal to 2, we would have to add some quantity to it. So that would be our slack variable. And finally, for x minus y, again, we have a greater than or equal to, so we will want to subtract a surplus variable. And then down at the bottom, we have minus 5x plus 8y plus p equals 0. And there's our system of equations. So now from there, we can set up our initial table. So the initial table will have an x column, it will have a y column, and then it'll have a column for every surplus and slack variable. So R, S, T, P, and then our constants. So in the X column, we have 2, 5, 4, -5. In the Y column, we have -1, 3, -1, 8. Now, in the R column, R is negative, so we have a -1, and we have no R's in the other positions. S is positive, and that only is in the second equation. T is negative, and that is only in the third equation. And of course, P is positive, and that is in the fourth equation. And our constants, 8, 2, 10, and 0. And then finally, we want to label our active variables R, S, T, and P. So that's the initial table. What we want to do now is to verify two things. Number one is that this is not the solution to the problem. This initial table is not the solution to the problem because we have a negative in the bottom row. So remember, from back when we first introduced the simplex method, anytime you have a negative in the bottom row, you are not at the solution. So we're going to have to create a new table. The other thing I want to point out, first of all, is that we have negative active variables. So let's just recall how we determine the value of an active variable. So the first active variable is r. So to determine the value of r, we go to the constant, which is 8, and divide it by the value in the r column and the r row, which is -1. That gives me r is equal to -8. And that's because we have the -1, the surplus variable, in that position. S is going to be that constant, 2, divided by 1, which is 2. T is going to be 10 divided by the number in the T column and the T row, which is a -1. So that gives me -10. So we have two negative active variables. So what we want to do is we want to identify those two. So I'm just going to put a little box around those two to tell me that those two active variables are negative. So to get started, we have to do what is called phase 1. And let's just get rid of some of this now. Phase 1 is what we do whenever we have a negative active variable. And so we have two negative active variables. To determine what the pivot is, we can go to either one of the rows that have a negative active variable. That would be either this row or this row. And we look for the largest positive number. All right, so if I use the first row, the R row, the largest positive number is in the X column. Well, if I go to the T row, the largest positive number is also in the X row. So either way I look at it, the X column, the X column is going to be my pivot column. This is how we determine the pivot column when we are doing phase 1. It's different than what we did with standard maximization and minimization problems, which is where we went to the bottom row and looked for the most negative number. The results may be the same, but they may not be the same. So the X column is my pivot column. And now to determine the pivot, it's exactly the same thing that we always do. We look for ratios. So we want a positive number. So the R row, we would have 8 divided by 2 is 4. In the S row, we would have 2 divided by 5. And then in the T, we would have 10 divided by 4. And so it looks like the smallest number is 2/5. So consequently, this is my pivot. The pivot is 5. Okay, that's really all I wanted to do in this video, is just show you how to get to the initial table, how to identify the negative active variables, and then how to determine what your pivot is. In another video, I will actually go through and continue solving this. So let's just do one more example. And let's say we want to minimize. I want to minimize C equals 3x minus 5y, subject to the constraints x minus y is less than 3 and 2x plus y is greater than 5, and x plus 8y is less than or equal to 1. Now, this is a non-standard minimization problem. Non-standard minimization problem. Right? Because we're asked to minimize, and we have mixed constraints. Whenever the constraints are mixed, it's going to be non-standard. Now, to solve a non-standard minimization problem, all we have to do differently is change the minimization objective function to a maximization objective function. And so what we're going to do is I'm going to say, okay, instead of minimizing c equals 3x minus 5y, we're going to maximize p equals, and we change the signs on the left-hand side, negative 3x plus 5y. Everything else stays exactly the same. We can rewrite this with the same constraints. X minus y is less than or equal to 3. 2x plus y is greater than or equal to 5. And x plus 8y is less than or equal to 1. So those are my constraints. Notice that the constraints do not change. The only thing that changes here is the objective function. And we're only changing the terms, the signs of the terms on the left-hand side. So what do we do from this point on? Well, to solve this problem, we set it up exactly like the last problem that I just showed you, like a non-standard maximization problem. So real quickly, we need to create a system of equations. So we would have x minus y with the 3 over here. And so this is a less than, so we would add a slack variable, 2x plus y. And this is a greater than, so we will subtract a surplus variable. And x plus 8y. And that is a less than, so we will add a slack variable. And then we would have 3x minus 5y plus p equals 0. And so that's our system of equations. And so from there, you would set up the table as in the previous problem. And that is the only difference with a non-standard minimization problem. All right, I don't want this video to get too long. I will do some more videos where I continue with some of these problems and actually work through them. But the idea here was just to get you started with the differences with a non-standard max and min.